Dijkstra's algorithm. History. What is the shortest way to travel from Rotterdam to Groningen, in general, from given city to given city? It is the algorithm for the shortest path, which I designed in about 20 minutes. One morning I was shopping in Amsterdam with my young fiancé, and tired, we sat down on the cafe terrace to drink a cup of coffee, and I was just thinking about whether I could do this, and I then designed the algorithm for the shortest path. As I said, it was a 20-minute invention. In fact, it was published in '59, 3 years later. The publication is still readable. It is, in fact, quite nice. One of the reasons that it is so nice was that I designed it without pencil and paper. I learned later that one of the advantages of designing without pencil and paper is that you are almost forced to avoid all avoidable complexities. Eventually, that algorithm became, to my great amazement, one of the cornerstones of my fame. Dijkstra thought about the shortest path problem when working at the Mathematical Center in Amsterdam in 1956 as a programmer to demonstrate the capabilities of a new computer called ARMAC. His objective was to choose both a problem and a solution that would be produced by computer that non-computing people could understand. He designed the shortest path algorithm and later implemented it for ARMAC for a slightly simplified transportation map of 64 cities in the Netherlands. 64. A year later, he came across another problem from hardware engineers working on the Institute's next computer: minimize the amount of wire needed to connect the pins on the back panel of the machine. As a solution, he rediscovered the algorithm known as Prim's minimal spanning tree algorithm, known earlier to Jarnik, and also rediscovered by Prim. Dijkstra published the algorithm in 1959, 2 years after Prim and 29 years after Jarnik. Algorithm. Let the node at which we are starting it be called the initial node. Let the distance of node y be the distance from the initial node to y. Dijkstra's algorithm will initially start with infinite distances and will try to improve them step by step. Mark all nodes unvisited. Create a set of all the unvisited nodes called the unvisited set. Assign to every node a tentative distance value. Set it to 0 for our initial node and to infinity for all other nodes. Set the initial node as current. For the current node, consider all of its unvisited neighbors and calculate their tentative distances through the current node. Compare the newly calculated tentative distance to the current assigned value and assign the smaller one. For example, if the current node is marked with a distance of 6 and the edge connecting it with a neighbor B has length 2, then the distance to B through A will be 6 plus 2 equals 8. If B was previously marked with a distance greater than 8, then change it to 8. Otherwise, the current value will be kept. When we are done considering all of the unvisited neighbors of the current node, mark the current node as visited and remove it from the unvisited set. A visited node will never be checked again. If the destination node has been marked visited when planning a route between two specific nodes, or if the smallest tentative distance among the nodes in the unvisited set is infinity when planning a complete traversal, occurs when there is no connection between the initial node and remaining unvisited nodes, then stop. The algorithm has finished. Otherwise, select the unvisited node that is marked with the smallest tentative distance, set it as the new current node, and go back to step 3. When planning a route, it is actually not necessary to wait until the destination node is visited as above. The algorithm can stop once the destination node has the smallest tentative distance among all unvisited nodes and thus could be selected as the next current. Description. Suppose you would like to find the shortest path between two intersections on a city map, a starting point and a destination. Dijkstra's algorithm initially marks the distance from the starting point to every other intersection on the map with infinity. This is done not to imply that there is an infinite distance, but to note that those intersections have not been visited yet. Some variants of this method leave the intersections' distances unlabeled. Now select the current intersection at each iteration. For the first iteration, the current intersection will be the starting point, and the distance to it, the intersection's label, will be 0. For subsequent iterations after the first, the current intersection will be a closest unvisited intersection to the starting point. This will be easy to find. From the current intersection, update the distance to every unvisited intersection that is directly connected to it. This is done by determining the sum of the distance between an unvisited intersection and the value of the current intersection, and then relabeling the unvisited intersection with this value, the sum if it is less than the unvisited int. In effect, the intersection is relabeled if the path to it through the current intersection is shorter than the previously known paths. To facilitate shortest path identification in pencil, mark the road with an arrow pointing to the relabeled intersection if you label/relabel it and erase all others pointing to it. After you have updated the distances to each neighboring intersection, mark the current intersection as visited and select an unvisited intersection with minimal distance from the starting point or the lowest label as the current intersection. Intersections marked as visited are labeled with the shortest path from the starting point to it and will not be revisited or returned to. Continue this process of updating the neighboring intersections with the shortest distances, marking the current intersection as visited, and moving on to a closest unvisited intersection until you have marked the destination as visited. Once you have marked the destination as visited, as is the case with any visited intersection, you have determined the shortest path to it from the starting point and can trace your way back following the arrows in reverse. In the algorithm's implementations, this is usually done after the algorithm has reached the destination node by following the node's parents from the destination node up to the starting node. That's why we also keep track of each node's parent. This algorithm makes no attempt of direct exploration towards the destination as one might expect. Rather, the sole consideration in determining the next current intersection is its distance from the starting point. This algorithm therefore expands outward from the starting point, interactively considering every node that is closer in terms of shortest path distance until it reaches the destination. When understood in this way, it is clear how the algorithm necessarily finds the shortest path. However, it may also reveal one of the algorithm's weaknesses, its relative slowness in some topologies. Pseudocode. In the following pseudocode algorithm, dist is an array that contains the current distances from the source to other vertices, i.e. dist2 is the current distance from the source to the vertex. The prev array contains pointers to previous hop nodes on the shortest path from source to the given vertex. Equivalently, it is the next hop on the path from the given vertex to the source. The code U vertex in Q with min dist2 searches for the vertex U in the vertex set Q that has the least dist2 value. Length V returns the length of the edge joining, i.e. the distance between the two neighbor nodes U and V. The variable alt on line 18 is the length of the path from the root node to the neighbor node V if it were to go through U. If this path is shorter than the current shortest path recorded for V, that current path is replaced with this alt path. 1 function Dijkstra graph source. 2. 3 create vertex set Q. 4. 5 for each vertex V in graph. 6 dist infinity. 7 prev undefined. 8 add V to Q. 9 dist source 0. 10. 11 while Q is not empty. 12 U vertex in Q with min dist2. 13. 14 remove U from Q. 15. 16 for each neighbor, V of U still in Q. 17 alt dist2 plus lengthu V, lengthu V, thu 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 V. 18 if alt dist, f dist, dist. 19 dist alt. 20 preview, 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 preview. 21. 22 return dist, prev. If we are only interested in a shortest path between vertices source and target, we can terminate the search after line 15 if U equals target. Now we can read the shortest path from source to target by reverse iteration. 1s empty sequence, 2U target, 3. If prevu is defined or u equals source, / do something only if the vertex is reachable. 4. While u is defined, / construct the shortest path with a stack stack S. 5. Insert u at the beginning of S / push the vertex onto the stack. 6. U prevu / traverse from target to source. Now, sequence S is the list of vertices constituting one of the shortest paths from source to target, or the empty sequence if no path exists. A more general problem would be to find all the shortest paths between source and target. There might be several different ones of the same length. Then, instead of storing only a single node in each entry of prev, we would store all nodes satisfying the relaxation condition. For example, if both R and source connect to target, and both of them lie on different shortest paths through target, because the edge cost is the same in both cases, then we would add both R and source to prev target. When the algorithm completes, prev data structure will actually describe a graph that is a subset of the original graph with some edges removed. Its key property will be that if the algorithm was run with some starting node, then every path from that node to any other node in the new graph will be the shortest path between those nodes in the original graph, and all paths of that length from the original graph will be present in the new graph. Then, to actually find all these shortest paths between two given nodes, we would use a path-finding algorithm on the new graph, such as depth first search, 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 search. Using a priority queue. A min priority queue is an abstract data type that provides three basic operations: add with priority, decrease priority, and extract min. As mentioned earlier, using such a data structure can lead to faster computing times than using a basic queue. Notably, Fibonacci heap Fredman and Tarjan 1984 or Brodel queue offer optimal implementations for those three operations. As the algorithm is slightly different, we mention it here in pseudocode as well. 1 function Dijkstra graph source, 2 dist source 0 / initialization, 3, 4 create vertex priority QQ, 5, 6 for each vertex V in graph, 7 if V source, 8 dist infinity / unknown distance from source to V, 9 prev undefined / predecessor of V, 10, 11 Q, and with prioritive dist, 12, 13, 14 while Q is not empty / the main loop, 15 UQ extract min / remove and return best vertex, 16 for each neighbor, V of U / only V that are still in Q, 17 alt distu plus lengthu V, lengthu V, thu 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 V, 18 if alt dist, alt dist, post, 19 dist alt, 20 preview, 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 21 Q decrease prioritive, alt, 22, 23 return dist prev. Instead of filling the priority queue with all nodes in the initialization phase, it is also possible to initialize it to contain only source. Then, inside the if alt dist block, the decrease priority becomes an add with priority operation if the node is not already in the queue. 198 Yet another alternative is to add nodes unconditionally. This can be done by additionally extracting the associated priority P from the queue and only processing further if P equals dist 2 inside the while queue is not empty loop. These alternatives can use entirely array-based priority queues without decrease key functionality, which have been found to achieve even faster computing times in practice. However, the difference in performance was found to be narrower for denser graphs. Proof of correctness. Proof of Dijkstra's algorithm is constructed by induction on the number of visited nodes. Invariant hypothesis. For each node V, dist is the shortest distance from source to V when traveling via visited nodes only, or infinity if no such path exists. Note, we do not assume dist is the actual shortest distance for unvisited nodes. The base case is when there is just one visited node, namely the initial node source, in which case the hypothesis is trivial. Otherwise, assume the hypothesis for n-1 visited nodes, in which case we choose an edge V where U has the least dist2 of any unvisited nodes such that dist2 equals dist plus length. Dist2 is considered to be the shortest distance from source to U because if there were a shorter path, and if W was the first unvisited node on that path, then, by the original hypothesis, dist would dist2, which creates a contradiction. Similarly, if there were a shorter path to U without using unvisited nodes, and if the last but one node on that path were W, then we would have had dist2 equals dist plus length with U, also a contradiction. After processing U, it will still be true that for each unvisited node W, dist will be the shortest distance from source to W using visited nodes only, because if there were a shorter path that doesn't go by U, we would have found it previously, and if there were a shorter path using U, we would have updated it when processing U. After all nodes are visited, the shortest path from source to any node V consists only of visited nodes, therefore dist is the shortest distance. Running time, practical optimizations and infinite graphs. In common presentations of Dijkstra's algorithm, initially all nodes are entered into the priority queue. This is, however, not necessary. The algorithm can start with a priority queue that contains only one item, and insert new items as they are discovered instead of doing a decrease key check whether the key is in the queue. If it is, decrease its key, otherwise insert it. 198. This variant has the same worst-case bounds as the common variant, but maintains a smaller priority queue in practice, speeding up the queue operations. Moreover, not inserting all nodes in a graph makes it possible to extend the algorithm to find the shortest path from a single source to the closest of a set of target nodes on infinite graphs, or those too large to represent in memory. The resulting algorithm is called uniform cost search (UCS) in the artificial intelligence literature and can be expressed in pseudocode as procedure uniform cost search graph. Start goal is goal is goal is goal is goal is goal is node start cost 0 frontier priority queue containing node only. Explored empty set. Do. If frontier is empty, then return failure or failure node frontier. Pop up. If node is goal, then return solution. Explored add node for each of nodes neighbors and do's and do. If it is not in explored, then frontier add in. The complexity of this algorithm can be expressed in an alternative way for very large graphs, when C** is the length of the shortest path from the start node to any node satisfying the goal predicate. Each edge has cost at least E and the number of neighbors per node is bounded by B. Then the algorithm's worst-case time and space complexity are both in a bon plus. Further optimizations of Dijkstra's algorithm for the single target case include bidirectional variants, goal-directed variants such as the asterisk algorithm CSS-related problems, and algorithms, graph pruning to determine which nodes are likely to form the middle segment of shortest paths reach-based routing, and hierarchical decompositions of the input graph. Combinations of such techniques may be needed for optimal practical performance on specific problems. Specialized variants, related problems and algorithms. The functionality of Dijkstra's original algorithm can be extended with a variety of modifications. For example, sometimes it is desirable to present solutions which are less than mathematically optimal. To obtain a ranked list of less than optimal solutions, the optimal solution is first calculated. A single edge appearing in the optimal solution is removed from the graph and the optimum solution to this new graph is calculated. Each edge of the original solution is suppressed in turn and a new shortest path calculated. The secondary solutions are then ranked and presented after the first optimal solution. Dijkstra's algorithm is usually the working principle behind link state routing protocols, OSPF and DYS being the most common ones. Unlike Dijkstra's algorithm, the Bellman-Ford algorithm can be used on graphs with negative edge weights as long as the graph contains no negative cycle reachable from the source vertex S. The presence of such cycles means there is no shortest path, since the total weight becomes lower each time the cycle is traversed. This statement assumes that a path is allowed to repeat vertices. In graph theory, that is normally not allowed. In theoretical computer science, it often is allowed. It is possible to adapt Dijkstra's algorithm to handle negative weight edges by combining it with the Bellman-Ford algorithm to remove negative edges and detect negative cycles. Such an algorithm is called Johnson's algorithm. The asterisk algorithm is a generalization of Dijkstra's algorithm that cuts down on the size of the subgraph that must be explored if additional information is available that provides a lower bound on the distance to the target. This approach can be viewed from the perspective of linear programming. There is a natural linear program for computing shortest paths, and solutions to its dual linear program are feasible if and only if they form a consistent heuristic, speaking roughly, since the sign conventions differ from place to place in the literature. This feasible dual/consistent heuristic defines a non-negative reduced cost, and an asterisk is essentially running Dijkstra's algorithm with these reduced costs. If the dual satisfies the weaker condition of admissibility, then an asterisk is instead more akin to the Bellman-Ford algorithm. The process that underlies Dijkstra's algorithm is similar to the greedy process used in Prim's algorithm. Prim's purpose is to find a minimum spanning tree that connects all nodes in the graph. Dijkstra is concerned with only 2 nodes. Prim's does not evaluate the total weight of the path from the starting node, only the individual edges. Breadth-first search can be viewed as a special case of Dijkstra's algorithm on unweighted graphs, where the priority queue degenerates into a FIFO queue. The fast-marching method can be viewed as a continuous version of Dijkstra's algorithm, which computes the geodesic distance on a triangle mesh. A triangle mesh. Dynamic programming perspective. Applications. Least cost paths are calculated, for instance, to establish tracks of electricity lines or oil pipelines. The algorithm has also been used to calculate optimal long-distance footpaths in Ethiopia and contrast them with the situation on the ground.